didn't they tried to mention it. The first one is work. What is work? And then in general, what is energy? Okay. And then what is power? And the different types of energy that we will be talking about. Kinetic energy, and there you have potential energy. Okay. You know, you will see it like in the video, you know, as soon as it gets uploaded. Then the term work is not really, you know, the term that we normally use it in our day-to-day life. It's not like like for instance, I'm sitting here and talking to you. You know, you may say like in our day-to-day language, like, okay, that's work. Actually, it's not in physics, like, because I'm sitting and I'm not moving. So in physics, work is basically what it says is there has to be force must act on an object. Okay, I'm just revising it, but you know, the details will be there. And then distance must be covered. Okay. So what do we mean by that? Then if you have a certain object, let's say chair or table, and then you apply force on it, are you guys following me? Then there has to be a certain distance that you need to cover. Okay, certain distance must be covered. Okay. Then when that happens, then work, abbreviated as uppercase W, is calculated as force times distance. Okay, the magnitude of the force multiplied by the distance. And then you can only apply this formula when F and D are in the same direction. Okay. When they are in the same direction. Alright. What do we mean by the same direction? What if they are not in the same direction? What if one is perpendicular to the other? So, not all forces do work. Okay, not all forces do work. So, the amount of work done by this force, for instance, then in this particular case, work done is 0. Why? If force and distance are perpendicular, right, perpendicular to each other, then work done is equal to 0. Okay, if F and D. Alright, so keep that in mind, like, you know. So for instance, you woke up in the morning, you picked up your backpack or your handbag, and then you got out of the house, and then you walked 2 miles, and then came back home. Then you dropped your backpack or your handbag. Then the only moment that you did work was when you lift up the bag. Why? Because, you know, if the bag was on the floor, when you lifted it up, you're applying the force. and then the distance is in the upward direction. But once you carry it, you are holding it like this. That means you are applying force, and then you are walking in this direction. So the force and the distance are perpendicular to each other. You're not doing any work. During this period, you haven't done any work. And then you came back, when you got home, like you're holding it, and then you're putting it back. So then you're dropping it, or you're putting it back slowly while you are holding it. Then in that case you are doing work. But otherwise, like if you carry a pail of milk and then walk around like a whole block in your neighborhood, then the amount of work done is zero. The only time that you did the work is like when you lift the pail. Okay, so then having said that, like you can already example 6.1 I already did it. So probably we can go ahead and then try to solve a few examples in the textbook. So I'm going to go and try to solve E1 at the end of the chapter. I'm going to read it. Okay, and then I'm going to give you a couple of minutes to solve it. E1 in the textbook, it says a horizontally directed force, so it says force, which is horizontal, is 40 Newton. Is used to pull a box a distance of 1.5 meter. Then how much work is done by this force? All of you got 1 minute. Actually, it's not that difficult. So work done is equivalent to force times distance. Your force is 40 Newton and your distance is 1.5. Then meter. Then work done is going to be 60 Newton meter. And this Newton meter has a special name known as joule. Okay, so keep in mind the SI unit. In the lecture video you will see it. The SI unit of work done is joule, and it's abbreviated as uppercase J. Okay, so yeah, that's correct. More example. Then E2, I'll read E2 for you. Again, you can pick the given parameters, and I'm going to give you a minute to try it. So E2 states a woman does 210 joules of work to move a table 1.4 meter across the floor. What is the magnitude of the force that the woman applied to the table if the force is applied in the horizontal direction? So now you're given as like work done 210 joules, distance 1.4 meter, 1.4 meter. Now how much force did she apply? Got a minute? Work done is equivalent to force times distance. Then to isolate force, you divide both sides by D. Then D cancels out. Then therefore your force is going to be work done, which is going to be 110 joules divided by 1.4 meter. And of course the SI unit, you can go through like the unit analysis, joule is Newton meter and so on and so forth, but but you already know the SI unit of force, which is Newton. So therefore we can just simply put the answer as 150 Newton. Simple. In a similar way, the other variety is like, what if you are asked to find the distance instead of if the other parameters are given. That's what E3 does. Okay. E3, so it has a given parameter. So the given parameter is like a force of 80 Newton used to push a chair across the room does 300 joules of work. So work done is now 320 joules. To move, so the force applied, again the force is parallel to the distance. Now how much distance? Okay, so find the distance. That's quick. Meters, because again work is equal to force times distance. Now we want to isolate the distance part, so you need to divide both sides by force. So distance is equal to 320 joules divided by 80 Newton. Then the Newton part will cancel out definitely within the joule, then we'll have 4 meters. All right. So now there is E5. Probably it's going to give us like a little interesting view of the just the problem, like the work example in general. That's what I mean. So now what it says is like a force of 130 Newton. So that's E5. A force of 130 Newton is used to drag a crate 4 meters across a floor. The force is directed at an angle upward from the crate, so that the vertical component of the force is 120. So the vertical component, I'm going to mention that, and then the horizontal component is 50. So the original force was actually 130 newtons. So the problem states the following: what is the work done by the horizontal component, what is the work done by the vertical component, and what is the total work done by the 130 Newton force. So it's being dragged and across for a 4 meter distance. So here is the question. I'll try to reframe it, and I want your full attention here. So you can imagine like one person can pull this thing with 130 newtons of force, at the way you see it, like with only this force. Or we can replace this 130 Newton force by 2 people. One person is applying 50 newtons of force in this direction. Another person is applying this much amount of force in the vertical direction. Okay. The eventual impact of the 2 forces is the same as the 130 single Newton force. I mean, I was trying to mention it like in the lecture video. I was trying to say like you have $1, like the paper money, okay, and then you replaced that with 4/4. Okay, what is the difference between those two? They both have the same value, they both have the same impact, they both can only buy the same kind of stuff, so the impacts are the same. The only difference is like, oh, one is paper money, the other one is coin. Okay, you see, it's like it's replacing one single paper money by 4 coins. Okay, this is what is happening. Like, instead of having this full 130 newtons of force, now it's replaced by 2 of its equivalent forces. So now question A asks, what is the force, the work done by the horizontal component? The horizontal component means this one. You can put it as FH, this one as FV, if vertical, that's what I mean. Then what is work done by the horizontal component? Answers? Got a minute to answer that? Let's see. The work done by the horizontal force is equal to, as you said, force horizontal multiplied by the distance that you move the crate across the floor. Then the force is 50 Newton, the distance is 4 meters. So work done by the horizontal force is 200 joule. Excellent, got it right. Now part B is asking you, like, how much work is done by the vertical component? Because the vertical force is perpendicular to the distance. The vertical force is acting perpendicular to the distance, because the distance is like the object moved along the floor in a straight line. So work done by the vertical component is 0 for a simple reason that like h, the force in the vertical, force in the vertical and distance are perpendicular. Okay, to each other. Now question C asks you the total work done by the 160, by work done by 130 newtons of force. That is simply adding what is its components are doing. How much work is the horizontal component doing? How much work is the vertical component doing? The horizontal component did 200 joules. The vertical component did another 0. So therefore the total work done by that 130 newtons of force is the same as the work done, the sum of the work done by its components, which is 100 joules, 200 joules. That's it. Okay. Yes. If the object is moving in the horizontal direction. In this particular case, the object moved along the floor. You see? See what I mean? Like the object is moving like in this direction on the floor. So when it's being pulled along the floor, it's moving in the horizontal direction. So the distance is only in the horizontal direction. And you can call it by definition, like in physics we define it like only the force component that is in the same direction as the force, or the force component that's the same direction as the distance, that the work. the force that is perpendicular to the distance doesn't do any kind of work. So that's how it's defined for us. Okay, it's a definition, it's a matter of definition. So if the force is always perpendicular, so for instance, like as you say, like, is it always the vertical force do a work? Of course it does. Like for instance, what if you lift up a certain object, like you picked it up from the floor and you move it, like for instance from here, so let's say, you know, to the back of your truck, let's see, you see, and in this case, like, you know, to the back of a truck, or you just simply lift it. Let's keep it simple. If you apply like 10 newtons of force, then it was on the ground, you lifted it up and put it on the top of a shelf, and the shelf is like 2 meters from the ground. How much work did you do? See, the force is in what direction? In the vertical direction. In what direction is the distance? It moved, the object moved in the vertical direction as well. So in this case, your work done is going to be just simply 10 times 2. Okay, so you're welcome. The force and the distances must be in the same direction to have a work done. Okay. Yes. You're welcome. Then the next item, you know, probably discussed in the video is something we call power. Okay, power. Power it's defined as like the rate of work done. How much work is done on an object, that is what power is. In general, like, you know, in terms of physics, you can find power as whatever work is done per time. Whatever work is done per time. Okay, so you know, you can imagine, like, you know, you raised a very interesting question. Like for instance, like, okay, let's say you picked up this and put it on the top of the shelf. Okay, let's say like you have hundreds of those, and you do it like 100 times. Pick, put, and then let's say you finish that work in 2 minutes. Okay, somebody else came in, 100 of those books, the same mass, same height of shelf, and then pick that one, put it up there, you know, each of them like one by one, and then this person took, let's say, 4 minutes. In layman terms, which person is more powerful? If you call this person A, and if you call this person B. Okay, excellent. So person A, right? Why? Because he was able to do the work in a shorter period of time. You know, you remember, like we were saying, the distance in this particular case is in the upward direction, and the person is going to apply force in the upward direction. Okay, so there is like force times distance being applied. That means work is done in a certain period of time. One did it in 2 minutes, the other person did it in 4 minutes. the more powerful guy is the A, the one who accomplished the work in a shorter period of time. Then as a result, like, power is equivalent to work done over time. How much work you can accomplish per unit time. Somebody who does the job at a faster rate is more powerful. Okay, so when it comes down to its unit, the unit of power is going to be joule per second, and that joule per second has a special name known as watt. So this unit of power is watt, and it's abbreviated as W. Okay, 1 joule over a second is equal to 1 watt. Okay, so keep in mind this W is for watt, it's not for work. Sometimes how do you differentiate it? If it comes after a number, it's a unit. So for instance, like if it says 1 W, then automatically this is watt, this is watt. But if you see like W is equal to F times D, this W is in a formula as a variable, this is work. Okay, if it comes right after a number, then definitely that's a unit. Okay, so then let me see if there's any power question we may be interested in, or maybe we can find something else. Okay, but also, like, I don't know if you also watched it, like no, the video isn't ready anyway. So you can also find power as force times average speed. Okay, there's also another formula for power, depending on like what is given. If work is given and time is given, then you can find the power by simply using that. Okay, but if it's like force and V, then you can just simply use that one. Okay, all right. Then we can go to energy. Okay, how energy is related to work done. Okay, so energy is defined as the ability to do work, right? Just the simple, very simple definition of work. Then probably back in your elementary science definition, kind of the ability to do work. But probably somebody never mentioned this work back then. Probably like it was expressed in terms of in terms of a slope, or in terms of pulleys, in terms of simple machine to facilitate work. But in general, how energy is defined as is like the ability to do work. We already mentioned it, and like in terms of work is already defined. It means force times distance and so on and so forth. But energy in general is the ability to do work. Like, how's energy related to work? I mean, just to give you an example, like for instance, you're driving a car, or you're in a car, and you're driving a car, or you can consider this like as if you are running, for instance. Maybe then like you had an initial velocity, right? Let's say 10 meters per second. And then you saw a dog crossing, and then you came to a halt, to a stop, right? Like you saw it accidentally, you know, pressed the brake, and then you stopped the car. And then let's say like you stop the car in this much distance. Okay. Now there was friction that helped you to stop it. Okay. Okay. So therefore, you know, there is work done by friction, can be considered as friction times distance. How much friction you had multiplied by distance. Then I'm going to come to the energy concept. Okay. So now they try to solve physical problems like that involves in terms of Newton's laws, right? We try to solve a few problems like in terms of Newton's laws and times something like that. But sometimes like Newton's laws might not be fully useful in certain instances. Okay. What if, let's say, you have a certain object or this car and it's moving, okay, and then let's say there wasn't any expression of like the acceleration of the object. If there's no any information about the time taken by the car to stop, if there is no any information about like how fast it was moving, I mean in terms of acceleration, if those kind of informations are missing, then Newton's laws might not be really as useful. So then that's why, like, you know, there is an additional concept known as energy. So the energy concept may express those things. So the very first kind of energy that we're interested in is kinetic energy. Okay. If an object has mass, and if an object has, you know, call it velocity or speed, then that object can do some work. It can do some work, I'm sure. Okay. It can do some work. Why? It can deliver energy with that mass and speed. It can deliver certain amount of energy. Then by having mass and speed, an object can have energy and it can do some work. Like, you know, for instance, you know, you drop you drop let's say your book or on top of a nail or hammer, right? So if you consider this a hammer, okay, when you move the hammer faster, the nail will go down faster. That means the head of the hammer had mass, and before the impact it had velocity or speed, and then it's doing work by driving the nail down. Okay. So the type of energy that you get by virtue of having motion is known as kinetic energy, and it's defined as kinetic energy is equivalent to half times mass times the speed or the velocity of the object or the car. Okay, so this is the definition of kinetic energy. It's one of the formula that I would put in my, you know, in my paper, in my formula paper that I prepare. Okay, so you need to prepare a formula paper. I mentioned this before. Yes. Yes. Okay. Yes. So this is your mass, because textbook chose to use V instead of speed, because kinetic energy is, it's a scalar quantity. the direction of the speed or the velocity doesn't really matter much. But let's use it as pretty much all the textbooks use v instead of the speed part. Okay, so mass times velocity squared divided by 2, that's what the kinetic energy of an object is. So that means when we come to here, you see the car started with a certain kinetic energy here, and it ended up with 0 kinetic energy. Okay, so then if you consider the changing kinetic energy, it means the changing kinetic energy of the car, where did it go? It did a work by the friction. The work done by the friction on the car resulted in the car to stop. In other words, work done on the car by friction is the same as the changing kinetic energy. The friction just did work. I put negative in there because of the friction is always in the negative direction. So it did work, and then it brought the car to stop. That means work done by friction brought changing kinetic energy. That's how they are related to each other. Okay, a little bit of the concept is important. That's why I just try to highlight it. But otherwise, we can go straight and solve an example. E7 in the textbook states 0.3 kilogram ball has a velocity of 20 meters per second. So E7. E7 says 0.3 kilogram ball. So you have the mass 0.3 kilogram. Has a velocity v 20 meters per second. Then question A asks you this: what is the kinetic energy of the ball? Gonna give you 1 minute to find that kinetic energy. 60 joules, 60 joules, 60 joules. All right. Okay. Very good. So this is just a direct application of the formula, right? So kinetic energy equals half times mass times v squared. So kinetic energy equals half, mass is 0.3, v is 20 squared. So kinetic energy would be half times 0.3, 20 squared is 400. Okay, since everything is given in SI units, because the mass is in kilogram, the velocity is given in meter per second, so therefore you keep everything in the way it is. So the answer for this one is going to be 60 joules. Very good. Okay, 60 joule. So there's a part B question. Okay. There's a part B question. So it states like how much work would be required to stop the ball. How much work would be required to stop the ball? Okay, how much work would be required to stop the ball? That means you need to find like work done on the ball. So you can literally consider that work done on the ball as the change in kinetic energy. Okay. So if you bring the ball to stop, what does it mean? That means its final velocity is what? Very good. Okay. So now you remember like the negative of the work done, right? On the friction on the car was equivalent to the change in kinetic energy. There's something we call it like work energy theorem. The textbook normally doesn't touch it that much. So therefore you are working against stopping the ball. So as a result, the negative work done that you do on the ball is resulting in what is the change in kinetic energy. So that means the negative work on the ball that you did to bring the ball to rest is its kinetic energy final minus kinetic energy initial. The final kinetic energy is 0 because you are bringing the ball to rest. Because of this, you bring it to rest. So therefore, the negative work on the ball, because of that energy theorem, the textbook doesn't text it, but it just randomly uses it. It has a full proof in a higher level physics, but we don't care much. minus the initial kinetic energy. The initial kinetic energy, we already got it like at 60 joule here. Initially it was moving at 20 meters per second anyway. So therefore what you need is like you need to do 60 joules of work to bring it to a height. Okay, so to stop it you need to do 60 joules of work. Okay, that's how like work. Maybe I'm not going to ask you a question like this, but I just want you to bring you up to speed from the very initial statement that we made, how work is related to energy with that kind of substance. Okay, it will be positive because in general, like the theory says, work done is equivalent to the change in the negative of the change in kinetic energy, because the negative, this you have negative here, you have negative here, they cancel out, and then eventually you do 60 joules of energy to, I mean work, to bring it to stop. It's like if the ball is a baseball, when somebody throws it to you, you need to do a work to bring it to stop. That means in general to catch it, because the ball is coming with a certain initial velocity, and then when you bring it to stop, its final kinetic energy is 0, right? So as a result, like you are doing a work, and that work is in general like it's a positive work that you did to bring it. It's not something an energy lost. In terms of energy lost, mostly we don't call it energy lost. Like for instance, work done on due to friction is considered as negative because it's always dissipating force. Okay, but otherwise in this particular case, your work, as the calculation shows, it's positive, then keep it as positive. Okay, those are very good questions. Then the next item is yes, we'll discuss it. All right, I will discuss that one in a moment. So the next item is another kind of energy. So that energy is gravitational potential energy. Gravitational potential energy, by virtue of having a certain height, by having a certain object at a certain height, let's say like you have an object at a certain height, so a book from a shelf or something like that, or a wrecking ball, if you are planning to wreck the floor, you let it drop. It does some work. That work, it can be in terms of damaging or driving in nails or something like that, but it is doing work. Okay, so then by having that height from the floor, then this mass can do work. That means it has an energy in it, and that energy is known as potential energy. So we're going to talk about the potential energy due to gravity. Spring has the same thing. If you compress a spring, what does it do? It recoils, and it does so every time when you compress it, it has a potential energy. That energy is a spring potential energy because it kicks back. If you put a ball next to a spring and you compress it and then you let it go, if that spring is strong and if it has like a good stiffness, then it can kick the ball, right? But let's just only focus on the gravitational potential energy. Then gravitational potential energy is calculated as mgh. The mass of the object, gravity, and then how high is the object. That's it. That's how you find the potential energy. And then let's go ahead and then maybe let's try to do an example. E8 says a box where the mass of 7 kilograms is lifted through a height of 1.5 in order to place it upon the shelf of a closet. What is the increase in potential energy? So E8 says like you have the mass, it is 7 kilograms, it's lifted through 1.5 meter. Then what is its potential energy after you lifted it up? How much potential energy did it gain? You have 2 minutes to answer. Yeah, the formula is this: mass times gravity times height. You're welcome. Yeah, you can use 10 gravity. Wonderful. So therefore potential energy is mgh. The mass is 7 kilograms. Everything is in SI unit. You don't need to make any conversion. And if you keep it that way, then the unit of energy is the same as the unit of work. Gravity is 10 meter per second square. Okay. Then your potential energy will be 105 joules. Yep, that's true. That's correct. Okay. Before we wrap it up, like then there is a conservation of concept known as conservation of potential energy, and we might not come across with I would say in exams, maybe. I mean, I don't know, but I'm not sure. But I want you to know, you know. So conservation. Conservation of mechanical energy. Okay. So what does it mean is like, you know, in the absence of friction, air resistance, you know, any drag force, okay, in the absence of friction, then mechanical energy is conserved. That means mechanical energy at one point, or initial, you can call it, is the same as mechanical energy at final. So what is this mechanical energy? Doesn't mean anything. It means just the sum of the potential and the kinetic energy. Potential and kinetic. Let me put it this way, maybe something that we usually understand. If you see, like, around our school there is a roller skating park, right, around BMCC, by the riverside. Then you see like kids playing like roller coaster and roller skating. So what happens is, like, if you see somebody who starts at a higher speed here, right, has a better chance to go at a higher elevation. If you have a high initial velocity here, then most likely you will end up at a higher height here. This can be explained in terms of, this is the height, of course. The height is just relative to where he started. This can be considered in terms of like mechanical energy. So if you look at this person, when he started here, he has kinetic energy, and that kinetic energy is maximum, because as you climb up you slow down, definitely, and the potential energy is literally zero. There was none. Why? Relatively, like, there is no any height here. He's on the flat part of the the park. But as he climbs up here, he comes up here, what happens to the potential energy? Now potential energy is max. His kinetic energy is now zero. Why? Because if you see them doing it, like, it goes up to a certain height and then they come back, right? Before they're coming back, they have to stop for a moment, right? So the kinetic energy there is going to be zero, because the final velocity is zero, then the potential energy is maximum. You see, what happened is, like, this total energy here transferred to, assuming there's no friction, completely transferred to potential energy. The kinetic energy here that you have a maximum, it completely transferred to a potential energy maximum. You may ask, how about in the middle, around here? He has both, a little bit of the kinetic, a little bit of the potential. Okay. Alright, so that's what is happening. And once he reaches up here, and then when he comes back, when it slides back, what happens? He had a potential energy. When he comes down to this level, he loses all the potential energy, and then he gains kinetic energy. See? So that's what the conservation of energy is like. Energy is conserved, like, in terms of potential energy. Same thing may apply for a pendulum. You hold a pendulum, you hold it right here, and then you let it swing. Swings, and then it will pass that, and then it will come to here. Let's say, this is relatively from the bottom part. You started it at 50 centimeters. What happens to the pendulum? Over here, you are holding it, and then it has maximum potential energy. When it reaches here, it's speeded the maximum, but it lost all the potential energy. And then what is left is like kinetic energy. And then when it swings to the other side, it loses its kinetic energy, and then it gains a potential energy. If there is no friction here, and if there is no any air resistance in the environment, this pendulum will go 50 centimeters to the other side. It starts with 50, it's gonna come to a 50 centimeter height. and then it will go back, and then it will regain that 50 on the other side. It will come here, and then it will swing back, and then it will go there, and so on and so forth. If there's no any air resistance, this pendulum will continue swinging back and forth forever, gaining that 50, losing that 50 to a maximum kinetic here, and then losing that kinetic here to a fully potential here, and so on and so forth. Okay, so since we already saw like the theory of like the simple harmonic motion yesterday in the lab, and there's a video for that, so for that we're not going to go back and talk about like the vibrating motion. So that's pretty much it, like for chapter 6.